Hello students. So up until last lecture we looked into an inequality of this type, where we had the lower bound of a function f defined on a closed interval a comma b is less or equal to the lower bound on all the subintervals, which is less than or equal to, of course, the upper bound of the function f on all the subintervals, which is less than or equal to the upper bound of the function f on the whole interval a comma b. Let us name this this relation so let us call this relation as equation 1. Now we define the upper sum. Now we define the upper sum of the function f corresponding to the partition P as we write u p f, which is equal to capital M1 times x1 minus x0 plus capital M2 times x2 minus x1 dot 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 up to capital Mn times xn minus 1. So you can write it as in the form of summation r running from 1 to n capital Mr xr minus xr minus 1. So this is our upper sum. Similarly, we can define our lower sum. So similarly, we can define our lower sum by similarly the lower sum is given by LPF, and you may have guessed it, it will be given by M1 times x1 minus x0, M2 times small m2 of course, x2 minus x1 dot dot up to Mn times xn minus 1. We can use the summation concept, and then it can be written as r running from 1 to n small mr times xr minus 1. So these two are basically called as the upper sum and the lower sum. Now each partition, so you see that each partition P belongs to this curly PAB, determines these two numbers. So determines these two numbers UPF and LPF, isn't it? So for every partition P, we will be able to get these points x0, x1, x2, x3 up to xn, and based on those points we can be able to obtain our subintervals x0 to x1, x1 to x2 and so on, and on each one of these subintervals we can be able to find our lower bound for the function f and the upper bound for the function f, mainly because the function f is bounded on a comma b, and based on that upper bound and lower bound on all of those subintervals, we can be able to calculate the upper sum, which is given by m1 times x1 minus x0 dot dot up to mn times xn minus 1, and we can be able to calculate our lower sum, which is given by small m1 times x1 minus x0 plus m2 times x2 minus x1 dot dot and so on. So each partition in this family of partitions will determine these two numbers, so UPF and LPF. You can see that they are basically numbers because upper bound and lower bound are numbers, and x1, x2, x3 are points on real line. So basically their difference is also a number. So ultimately we are obtaining two numbers with the help of this partition P. All right. So, now what we have is, let us go to a new page. So, now what we have is from inequality 1. So, from inequality 1, where is that? Let us go back to the previous slides. Okay. So, in this slide, from inequality 1, we have small m less or equal to mr less or equal to capital Mr less or equal to m. So, we will write that inequality. So, small m less or equal to mr less or equal to capital Mr less or equal to capital M, and we will multiply this whole inequality by xr times xr minus 1. Let us multiply So, as I was saying that xr and xr minus 1, they are both points on real lines. So, their difference is also a real number basically. Now, even if you have a negative interval, that means minus 1 to minus 2, and if you divide it into equal subintervals, you will still get this difference as a positive. So, xr minus 1 is always a positive number, and that is why when you multiplied the inequality, when you multiplied this inequality here, this inequality, the inequality sign did not change. All right. So, next we will take the summation on both sides. So, this is true for every r running from 1 to n. So, if I take summation on both sides, so this will be summation r running from 1 to n m into xr minus 1, summation r running from 1 to n small mr times xr minus 1, which is less or equal to summation r running from 1 to n capital Mr times xr minus 1, which is less or equal to sum r running from 1 to n capital M times xr minus 1. So, here in this sum on the left hand side, here in this sum, small m is independent of r basically because small m is the lower bound on the whole interval a b. So, it's not relevant to each one of those subintervals. So, you can take that m out of the subinterval, and then it will be basically sum r running from 1 to n xr minus 1, which is less or equal to sum r running from 1 to n small mr xr minus 1, which is less or equal to sum r running from 1 to n capital Mr times xr minus 1, which is less or equal to sum r running from 1 to n xr minus 1, and here also we take capital M out of the interval because capital M is also independent of r. Now, here what we are basically doing, we are basically summing the difference of all the subintervals. So, that means we are subtracting x0, we are subtracting x1 minus x0 plus x1 minus so plus x1 minus x2 plus x2 minus x3. So, if we expand this summation, then you will be able to notice that except xn minus x0, all other points cancels out. So, if you expand the summation, you will be able to see that, and ultimately we will be left with xn minus x0. Similarly, here this term is defined as the lower sum LPF if we look into the previous slide. So, here, so LPF is defined by this sum here. So, we can write it as LPF, and this sum is defined as UPF. So, UPF, and here it is basically capital M times again xn minus x0, and this xn minus x0, we know that xn is our point B and a0 is our point A, is less or equal to LPF is less or equal to UPF, which is less or equal to capital M times b minus a. So, here what we have is basically an inequality which is also important. So, this inequality says that your lower sum and your upper sum will be bounded by small m times b minus a. So, basically the lower bound of the function f on the closed interval a b times the difference of the endpoints basically, and the upper bound is capital M times b minus a, which means that the upper bound of the function f times the difference of the endpoints will be an upper bound for your lower sum as well as the upper sum. So, this is the second inequality which we needed to establish before we go to the Riemann integrable functions. Now, based on this, we can define two numbers. So, the first number is so we have basically, so here we have two sets of real numbers. So, one is as we said, every partition P determines UPF, and we have LPF for every partition P in that family of partition AB. So, basically we have two sets of real numbers for every partition P in that family of partitions, and the supremum of this set LPF. So, the supremum of the set LPF such that P is in curly P of AB is called as the lower integral of f on the closed interval a comma b, and it is denoted by integral from a to b. We put a small minus sign here just to signify that it is a lower integral fx dx, or you can shorten it by a to b f dx, or we can even shorten it by integral from a to b simply f. So, when I write integral from a to b just f, it basically means that integral from a to b, lower integral of course, fx dx. This is just one of the notations to save time in a way. Now that we have the lower integral, we can also define the upper integral. For the upper integral, let us go to the next page. Okay. The infimum of the set all those UPF such that P is in curly P of AB is called as the upper integral of f on the closed interval a comma b, and we can write this upper integral, and it is denoted by integral from a to b. We put a dash sign or a minus sign in the upper limit f(x) dx, or we can write it as a to b f dx, or to save time we can even write a to b simply f. So, based on the upper sum and lower sum, we can be able to define the upper integral and the lower integral. They are also sometimes called as upper Riemann integral and lower Riemann integral. Now, that the definition of the upper integral and lower integral are given, and we have also given the notations. We can define the Riemann integrable function. So, definition a function f or a bounded function f, on the closed interval a b is said to be Riemann integrable if both lower and upper integral. Let us follow one notation. So, I am removing this dx here. So, lower integral and upper integral exist, and they satisfy this relation. So, the lower integral and the upper integral has to be equal. Then such functions are called as Riemann integrable function, and the common value of this to this is called the Riemann integral of f on this closed interval a b, and it is denoted by a to b f. f(x) dx, we can write it f(x) dx, or we can shorten it like before simply by a to b f dx or a to b f. So, in order to talk about the Riemann integrability, you see that we had to first look into the concepts of partition, that how you get the partition of a closed interval. Then from that partition we formed non-overlapping subintervals. Based on those subintervals, we could be able to define those lower bounds and upper bounds, not only for the function on the whole interval, but also on those subintervals. And for every such partition, you will get a different type of non-overlapping subintervals, and then you get different types of lower bounds and upper bounds on those subintervals. Now, once we have those lower bounds and upper bounds, we were able to obtain the lower sum and the upper sum, and based on those lower sum and upper sum, we can be able to obtain this lower integral and the upper integral. And if those lower integral and upper integral are same, then in that case we say that the function is Riemann integrable. Here the upper sum and the lower sum, they depend heavily on what kind of partition you are choosing. So, for every partition P of this family of partitions, we can be able to obtain this upper sum and lower sum. So, these are basically two sets of real numbers depending on the partition P, and based on those two real numbers, which is lower sum and upper sum, we can be able to define the lower integral and the upper integral for the function f. And if those lower integrals and upper integrals are same, then in that case the function is said to be Riemann integrable and they are common value. That means when they are equal, then that particular value is called as the Riemann integral of the function f on that closed interval a b, and we use a a simplified notation in a way, integral simply integral from a to b f x dx. So this is just a preparation to define the Riemann integral or Riemann integrable functions on a closed interval a comma b. We will look into now an example where we will show that a function is Riemann integrable. Before I proceed any further, I have provided you a list of references where you can look into for the details, the things which I am teaching. Most of the time I will try to follow my own lecture notes. I have prepared my own lecture notes which I will follow, and I will also try to give you some examples based on the concepts which I am teaching, and hopefully that will help. So now we will look into one example where we will show that a given function is Riemann integral or Riemann integrable or not. So let's start with example 1. So statement, let a comma b be a closed and bounded interval in set of all real number R, and C is any arbitrary point or number in R, and let f mapping from a to b to R be defined as f(x) equals to c for all x in a comma b, then prove that f is Riemann integrable. All right. So we'll look into the solution. Before we start solving this problem, we first have to just gather the ingredient. What do we need to show the Riemann integrability? So we have to show that the lower integral is equal to the upper integral. Now in order to obtain the lower integral or upper integral, we first have to obtain the lower sum and the upper sum, and before we can obtain the lower sum and upper sum, we first have to find out a partition for this closed interval a comma b. Based on that, we have to find out the lower bound and the upper bound for this function f on those subintervals as well as on this closed interval a comma b. Here we are a little bit in luck because the given function is constant. So for the constant function, it doesn't matter what kind of partition or what kind of points you are choosing, the value would remain always the same. So that means the lower bound and the upper bound would always be same, not only on that closed interval but also on those subintervals as well. However, just to make things clear or the concept clear, we are going to solve this example. So let's see. First of all, f is bounded. So f is bounded on a comma b, and let us take a partition. Let us take a partition P of a comma b as x0 to x1 dot so x0 to x1 to xn where a is x0 less than x1 less than dot dot up to xn equals to b, and obviously the sub intervals would be x0 to x1, x1 to x2, dot dot and so on up to xn minus 1 to xn, and let capital M be the supremum of the function f(x) on this closed interval a comma b, and small m is the infimum of the function f(x) on this closed interval a comma b. Similarly, we define capital Mr as the supremum of f(x) on xr minus 1 to xr, and a small mr as the infimum of the function f(x) on the interval xr minus 1 to xr. By the way, if I don't write x belongs to xr minus 1 to xr, like the way I have written here, it always means that x is in xr minus 1 to xr, where r is running from 1 to 3 dot dot up to n. So, since f is a constant function, its upper bound and the lower bound would always be same. Not only that, it will be same on that on those sub intervals. So, since f is a constant function, our capital M, the upper bound, is basically the constant c. Our lower bound on the whole interval a b is again c. Our upper bound on each one of those sub intervals is c, and our lower bound on each one of those sub intervals is again c, where r is running from 1 to 3 up to n. So, based on that, I can calculate my upper sum UPF, which is basically sum r running from 1 to n capital Mr xr minus xr minus 1. So, capital Mr is basically c. So, c will come outside of the summation because it is independent of r, and here we will have xr minus 1. Now, again this is similar to what we have done we did earlier. So, if you expand the summation, then you will basically have xn minus x0 left. So, we will have xn minus x0 left. Xn is basically our b and x0 is basically our a. Similarly, we can calculate our lower sum, which is r running from 1 to n small mr xr minus xr minus 1. This is c times r running from 1 to n xr minus xr minus 1. Similarly, this will also give c times xn minus x0, and therefore, we will obtain c times b minus a. All right. So, now let p be let us consider the set of all partition, the set PAB of all partitions of a comma b. Then basically it follows that the set LPF, where all such p is in curly p of AB, and the set UPF and the set UPF, where p is in curly p of AB. I mean, they are both basically how to say, the singleton set are the singleton set are the singleton set c times b minus a, because it does not matter what kind of partition you will choose, since it is a constant function we will always obtain c times b minus a, and therefore the least the how to say, the supremum or the infimum, that is the least upper bound or the least or the how to say, the greatest lower bound will be always c times b minus a. So, like we were talking about the supremum of LPF and infimum of UPF, if we take for these two sets, actually it will always be so what I am trying to say is supremum of all such LPF such that P is in curly P of AB will be c times b minus a, and infimum of all such UPF such that P is in curly A of comma B is again c times b minus a. So, that means the lower integral. So, that is the lower integral and the upper integral are same, which means integral a to b f is equals to integral a to b f is equals to c times b minus a, and since they have a common value which is basically c times b minus a, this is the Riemann integral of the function f on the closed interval a b. So, this means that c times b minus a is the Riemann integral of f on a comma b, where f is the constant function, and it is denoted or we can just leave it like that. So, for this constant function f is equals to c, we were able to show that this constant function is Riemann integrable on the closed interval a comma b. For that, of course, we needed to calculate the upper sum and lower sum, which was basically c times b minus a, and if we take the supremum of all such upper sum of all such lower sum and the infimum of all such upper sums for all for over the I mean, how to say, set of all these partitions, then you always get it as a c times b minus a. We will always get it as c times b minus a, and since the lower integral and the upper integral is same, this common value is basically the Riemann integral of this function f on this closed interval a b. We will look into one more example in the next lecture, and we will conclude today's lecture on this example. So, thank you for your attention.